Welcome back to the deep dive. Today, we are cracking open a utility that is absolutely foundational to modern computing, yet often operates, entirely invisibly, running quietly in the background of almost every data center, lab, and embedded systems project worldwide. We are talking about QEMU, the Quick Emulator.
And calling it just an emulator is perhaps the greatest disservice to this piece of software.
Yeah.
I mean, if you've launched a virtual machine in the cloud, if you've done development for an ARM chip on an x86 laptop, or maybe spun up a quick testing environment, chances are you were interacting with QEMU.
Right.
It's far more than some niche tool. It's a critical open source utility,
Yeah.
and it has this dual role that secretly powers everything from, well, low-level silicon testing right up to the back ends of major cloud virtualization platforms.
That dual identity, that's really the absolute key to understanding its architecture, isn't it?
Yeah.
QEMU serves two profoundly different masters. On one hand, it is the purest form of digital impersonator, a full cross-architecture emulator, able to translate software compiled for one instruction set architecture, or say AR, to run on a completely different physical architecture like x86.
Right.
But then on the other hand, it acts as this versatile virtual machine manager, a VMM, and also a device emulation backend that supports hardware acceleration, which makes it, well, lightning fast sometimes.
Exactly, and that's the tension we really need to analyze today. QEMU's fundamental design conflict is maximizing compatibility, running anything, anywhere, while simultaneously trying to maximize speed, which means getting near-native performance.
And you just can't achieve both at the same time.
Nope. That inherent tension forces QEMU onto a very specific kind of sliding scale of capability and compromise.
So what does this deep dive mean for you, the listener? Our goal today is to really analyze where QEMU makes its architectural stand. We need to define precisely when a system designer or maybe a developer must accept that severe performance trade-off for cross-platform flexibility.
And conversely, what hidden architectural costs pop up when you prioritize maximum near-native performance. It's a core decision point for anyone working with modern virtualized infrastructure, really.
Okay, so to truly appreciate QEMU's hybrid genius, we have to start by drawing a really clear line between the two main ways we run software in a virtual environment: emulation and virtualization. Let's start with the one QEMU is named after, the digital impersonator, emulation.
Right. Emulation is, well, it's the hard way. It's about building a complete full system model entirely in software. You are recreating the entire system behavior, register by register, maybe even cycle by cycle, simulating the exact hardware the original software was designed for.
So the emulator acts as a translator, essentially.
Pretty much, it's a software translator layer. If you have software compiled for, say, MIPS ISA, and you want to run it on a x86 host, the emulator has to translate every single instruction in real time.
So the goal is just total compatibility, right? You want that emite software to execute unmodified, even though the underlying physics of the machine are completely different.
Precisely. You get the immense benefit of universal compatibility. You can bridge any architectural gap. But the cost? Well, the cost is the heavy lifting of that translation layer. Imagine every single machine instruction needing real-time interpretation.
Yeah, sounds intensive.
It requires significant computational effort and generates enormous performance overhead. It is a functional requirement in that case, not really a choice.
Okay, now let's contrast that with virtualization, what we could maybe call the partition model.
Virtualization is fundamentally different because it's not about translation, it's about partitioning. The system uses a hypervisor, and crucially, it leverages built-in hardware extensions, things like Intel VTX or AMD-V.
The hardware hooks.
Exactly. The guest system is then allowed to run directly on the physical hardware in what we call Ring 0, the most privileged operating mode. The hypervisor only steps in for, sensitive operations.
And that's where we get that superior performance, often reaching near-native speeds. It feels almost instantaneous sometimes.
It is almost instantaneous because there's practically no translation overhead for the CPU.
Right.
But here is the critical constraint, and this is what really defines the limits of virtualization. Platform dependency.
Meaning,
to achieve this high speed, the guest architecture must match the host architecture. And by 8664 guest needs a by 8664 host. A modern ARM v8 guest needs an ARM v8 host. You are simply partitioning the same kind of hardware. You're not interpreting different hardware.
This sounds like a strict dichotomy then. Either you choose low compatibility with emulation, or you get fast, same architecture speed with virtualization. So how does QEMU, which we call the hybrid, fit into the strict either choice.
This is QEMU's core genius.
Decoupling.
It separates the highly performance-sensitive CPU execution task from the crucial, complex, and highly adaptable job of device emulation.
Okay.
QEMU basically decided that if system architects need near-native speed, QEMU will just step away from the slow software translation job altogether.
And instead, what does it do?
Instead, it acts purely as the virtual machine manager, the VMM. It handles configuration, boot, the management interface. But most importantly, it becomes the robust device emulation backend. It delegates the heavy lifting of the CPU execution to specialized hardware virtualization accelerators, or HVAs, like KVM on Linux.
So QEMU keeps the parts that need maximum versatility, like the virtual hard drives, network cards, USB controllers, the BIOS, and it just hands off the speed requirement to specialized hardware assistance when it can.
Exactly. This hybrid approach is what gives QEMU its longevity. It strategically captures the speed of hardware acceleration when possible, while still maintaining its universal capabilities in device abstraction and machine management. It provides the standardized virtual environment, regardless of whether the CPU is being run by QEMU's own slow software translator or by, say, KVM's near-native hardware pass-through.
I think this is what confuses people who are new to virtualization sometimes. QEMU isn't just an emulator that can run slow. It's a VMM that can run fast, because it knows when to delegate its core CPU responsibility to something like the kernel.
That tension between maximum compatibility using its own software translation, TCG, and maximum performance using a partner like KDM, that really defines the entire operational spectrum. If you're testing some niche embedded system, you live in the slow, compatible mode. If you're spinning up 1,000 cloud containers, you live in the fast, delegated mode.
Right.
The architectural decision is always dictated by your workload's priority, compatibility or speed.
Okay, let's break down the two primary functional modes in which QEMU operates, starting with maybe the simplest, most developer-centric option, user mode emulation.
Yeah, user mode emulation is a very focused, targeted approach to cross-platform execution. Its function is pretty narrow. It translates and runs specific application binaries, typically programs compiled for Linux or maybe macOS for a foreign ISA, without all the overhead of modeling a full virtualized operating system or a BIOS or devices.
So if I'm on my x86 machine and I have an application compiled for ARM, I just point QEMU at the binary. Is it that simple?
In essence, yes. The process involves dynamically translating the guest program's instructions into host instructions on the fly. And crucially, it also performs what's called syscall translation, or sometimes punking.
Syscall translation.
Yeah, it translates the operating system calls, the requests the application makes to the kernel for services like file access or memory allocation. It translates those from the guest's format into the host's kernel format. It also has to handle things like endianness differences, or maybe 32-bit versus 64-bit addressing, all on the fly.
Wow, this must be absolutely essential for development teams that cross-compile software.
Absolutely. The main use cases are cross-platform software development, quickly testing tool chains by executing binaries compiled for a different target, and actually a lot of security research.
Oh, interesting. How so?
Well, security analysts frequently use this mode to analyze foreign architecture binaries. Maybe malware that's intended for an embedded ARM device, but they analyze it safely on their powerful x86 analysis machine.
But you mentioned earlier this mode is not self-contained. That sounds like a pretty critical dependency developers need to be aware of.
It is. It's the single biggest operational caveat, really, for dynamically linked binaries, and that's most of them. QEMU doesn't virtualize the supporting libraries. It actually relies on the host environment to provide the target architecture's shared libraries, like libc.so.
Wait, so if I want to run that ARM binary on my x86 host, I have to somehow manually install the ARM version of all the required libraries onto my x86 machine first?
Correct. You have to configure the host environment to point QEMU toward the correct cross libraries, typically using an environment variable like QEMU prefix.
Huh.
This whole provisioning step means that user mode emulation offers basically no real isolation benefits. You are relying heavily on the host system's configuration, making it functionally quite similar to a standard root environment, but you've got the added complexity of instruction translation on top.
Okay, got it. Now let's pivot to the grander, more complex side, full system emulation. This is QEMU acting as a true modeler of the entire machine, not just an app launcher.
Right. Full system emulation provides a complete virtual model of an entire computer system. This means CPU, network, storage, memory, and critically, the firmware like a virtual BIOS or UEFI, often utilizing components like cBIOS for x86 systems. This robust model allows an unmodified guest OS to boot and run, thinking it's on actual physical hardware.
And this is where QEMU's architectural breadth becomes, well, frankly, staggering.
It truly is. I mean, our sources confirm QEMU supports ISAs ranging from the ubiquitous by 86 and by 8664 through industrial standards like MIPS, the globally dominant mobile and embedded architectures ARM-v7 and ARM-v8,
Wow.
legacy enterprise systems like PowerPC and SPARC, IBM's mainframe architecture S390X, and even the future-focused open-source ISA NV. This breadth is what makes QEMU just indispensable for simulating both, obsolete legacy hardware and emerging architectures.
And this full system modeling, that's the foundation of QEMU's device abstraction layer, even when it's running in the fast accelerated mode with KVM, right?
That's vital, yes.
Yeah.
Even when KVM is handling the CPU, QEMU remains responsible for managing all the peripherals and I/O. And this device modeling layer is powerful enough to support really modern concepts like confidential guest support, protecting memory from the hypervisor, and the use of pair virtualized I/O via VirtIO devices, which helps ensure I/O performance can actually scale with CPU speed.
So if we kind of synthesize this, we have a clear operational spectrum defined by that trade-off we talked about right at the start, compatibility versus speed.
We do. We basically have three distinct points on that scale, each with a different compromise. First, pure TCG, full system. This guarantees maximum cross-architecture capability, any ISA on any ISA. But it is the slowest performance profile because the CPU relies entirely on QEMU's own software translation, its dynamic binary translation, or DBT.
Okay, slowest but most compatible.
Right. Second, HVAK-VM, full system. This is the performance king. It's limited strictly to same architecture operation, by 86 on by 86, ARM on ARM. But it delivers near-native speed via hardware acceleration.
Fastest but least flexible architecturally.
Exactly. And third, user mode. This offers cross-architecture capability, but only for specific applications. It's moderately faster than TCG system emulation because it skips modeling the entire OS and devices, but it still incurs that overhead of instruction translation and the syscall thunking we mentioned.
So if I absolutely must run, say, a proprietary SPARC system from the 1990s on my modern Intel server, I have no choice but to accept the slowest profile, pure TCG.
That is the architectural dictum. You buy compatibility with speed, or you gain speed by sacrificing cross-architecture flexibility. And understanding why that pure TCG mode is so slow, well, that's the next critical piece of the puzzle.
The tiny code generator, or TCG. That really is the beating heart of QEMU's cross-architecture magic, isn't it? It's what gives QEMU its title as the universal translator. But as we keep mentioning, it carries the largest performance weight. Let's dive deep into its internals to understand that bottleneck.
Right. TCG is QEMU's implementation of dynamic binary translation, or DBT. It doesn't translate the entire guest program ahead of time. It only translates instructions when they are encountered for the first time during execution. This translated code is converted into executable host instructions and stored in these reusable chunks called translation blocks, or TBs.
So if the same piece of code is executed multiple times, it only has to pay that translation cost once?
Precisely. That caching is fundamental to making it usable at all. But the real genius, and also the source of its immense portability, lies in its translation pipeline. As you noted, QEMU doesn't translate, say, MIs directly to by86, and then SPARC directly to ARM, and so on.
Yeah, that would be unmanageable.
It would require writing and maintaining n times m translators, where n and m are the number of supported architectures. It'd be completely impossible to maintain.
So how does QEMU manage to support nearly a dozen different processor architectures then?
It uses an intermediate representation, or IR architecture. Think of the IR as a kind of standardized internal neutral language, like the Esperanto of processor instructions.
Okay.
QEMU translates guest IS, architecture agnostic IR, host IR.
That sounds brilliant from a development standpoint. If a new architecture like RSCV emerges, QEMU only needs to write the front-end bit, RISCV to IR, and then it can reuse all its existing backends, IR to by86, IR to RM, etc.
It scales compatibility horizontally with minimum development effort. It's the reason QEMU has survived for decades and is still the dominant player in cross-architecture emulation. It definitely prioritized ease of development and massive breadth over, hand-tuned performance for specific pairs.
Okay, now for the painful truth. Why does this architectural decision, this brilliant IR layer, create such a massive performance bottleneck?
Well, because the IR has to be generic enough to represent any instruction from any supported ISA. By its very nature, this generic language cannot take full advantage of the specific, highly optimized instructions or features present in the specific host CPU you're running on.
So complex operations get broken down.
Right. Every complex guest operation potentially has to be broken down into multiple, simpler, generic IR instructions before being reassembled into host code. This just introduces inefficiency at multiple steps.
Can we quantify that inefficiency? Our sources mentioned a pretty huge number.
Yes, the empirical data is, well, it's stark. Proof-of-concept emulators that have been designed specifically to bypass the IR entirely, focusing only on one specific guest-to-host translation, like ARM to BEC86, have demonstrated execution speeds up to 35 times faster than QEMU operating solely with TCG.
35 times faster. Wow. So to put that in perspective, if a task takes 1 second on native hardware, it might take 35 seconds in pure QEMU TCG mode. That's a profound performance penalty.
It is the concrete price of portability. TCG inherently sacrifices absolute execution speed for maximum universality and ease of maintenance. This is the trade-off every developer using cross-architecture emulation must understand. You are paying the portability tax, and it's a hefty one.
Given that tax, what strategies are employed within TCG to try and claw back whatever performance gains they possibly can?
Well, they fight tooth and nail against runtime overhead. One area is CPU state optimizations. Inside each translation block, QEMU tries to track the virtual CPU state. For instance, in by86 architecture, memory addresses often involve segment-based additions.
Oh, okay.
If the translator detects that a particular segment register is 0, which is actually a common optimization, it can eliminate that addition instruction entirely from the translated host code, generating much cleaner, faster code.
Right.
They only invalidate those translator blocks when the relevant CPU state truly changes, avoiding expensive retranslation whenever possible.
Okay, that minimizes retranslation. What about keeping the code execution flowing smoothly? That's where the dispatcher comes in, right? The main loop.
That leads to direct block chaining, which is arguably the most crucial internal speed-up technique. Normally, when one translation block finishes executing, the control returns to the main QEMU dispatcher loop. This loop has to check for interrupts, exceptions, pending events, all that stuff.
Right.
Block chaining allows the host CPU to jump directly from the end of one translated block to the start of the next sequential block without going back to that centralized dispatcher loop.
That sounds like bypassing a central traffic control tower every time you want to drive from one block to the next.
Yeah.
Saves a lot of overhead.
Precisely. Bypassing that intensive reevaluation step for every single block dramatically reduces the overhead associated with context switching and loop management. It leads to significant throughput gains when you're running long sequential code paths.
And what about the notorious headache of self-modifying code, or SMC? How does TCG handle that?
Oh, SMC is a massive challenge, particularly on older architectures like by86, where it was more common. The guest application changes its own instructions in memory, but the guest hardware doesn't necessarily signal a cache invalidation to let the emulator know.
Tricky.
So QEMU has to constantly monitor memory writes. If a write operation overlaps with an existing, already translated TV, QEMU must immediately detect that modification and invalidate the corresponding translated block to ensure execution integrity. If it misses this, well, the system runs stale, incorrect code, leading to crashes or wrong results.
It sounds like QEMU spends an extraordinary amount of effort basically fighting its own portability architecture to gain speed.
It really does. An analysis of QEMU's performance profiling shows something kind of surprising. Most of the time is actually spent executing the already translated code, not in the JIT compilation process itself.
Oh, interesting.
This means future optimization efforts are focused less on making the TCG compiler itself faster and more on improving the quality of the generated host code and reducing the runtime overhead associated with managing the dispatcher and the translation block lookups. They're trying to squeeze every last cycle possible out of that potential 35x performance gap.
Okay. The moment you realize TCG introduces a potential 35-fold performance penalty, you immediately understand why large enterprises and cloud providers just cannot rely on it for production workloads. Speed has to come from somewhere else.
Absolutely.
And that pivot takes us directly to QEMU's strategic partnership with hardware acceleration mechanisms.
Right. This transition is where QEMU changes hats, really. It goes from being a pure software emulator to acting as a high-speed system orchestrator. When the host machine has the necessary hardware assistance, Intel VTX, AMD-V, or their ARM equivalents in the QEM, leverages kernel modules like KVM on Linux. This creates that essential hybrid model we touched on earlier.
KVM, the kernel-based virtual machine, is often confused with QEMU, but they're distinct. What exactly is KVM's specialized role in this partnership?
KVM integrates deeply into the Linux kernel and functions as what's called a Type 1 hypervisor. Its role is actually highly focused. It handles processor virtualization and memory management directly using those hardware extensions.
Because in the kernel.
Yeah, since it operates in the privileged kernel space and accesses hardware extensions directly, it achieves near-native performance. KVM handles the CPU, essentially letting the guest CPU run directly on the host silicon with minimal intervention.
Okay, so if KVM handles the processor, what is QEMU doing in this scenario? Is it just sitting there?
Not at all. QEMU becomes the virtual machine manager, the VMM. It handles all the critical configuration, splitting up the VM, managing all the command line parameters, handling the management interfaces, which we'll get to later, and most critically, providing the robust, standardized emulation of all the non-CPU hardware devices and I/O.
Ah, so the virtual network cards, storage controllers, graphical output, that's all still QEMU's job.
Yes, exactly. QEMU provides the stable virtual hardware platform. KVM provides the CPU speed.
This sounds like the optimal model then, the best of both worlds.
Yeah.
But it still runs into that architectural constraint we defined way back in Section 1.
That constraint is the absolute gatekeeper of speed here. Hardware accelerators, whether it's KVM or HVF on macOS or WHPX on Windows, they all operate under one strict rule. The guest ISA must match the host ISA.
Right.
An x86 host running KVM can only accelerate an x86 guest. An ARM host running KVM can only accelerate an ARM guest.
So performance is maximized only in these architecturally homogeneous environments. If I try to run a foreign ISA, like ARM on x86, KVM just steps back.
KVM can't help. QEMU is immediately reverted to using its own much slower TCG mode for the CPU translation. That's the hard truth.
So if I'm a developer running a massive regression test suite for ARM targets and I demand performance, there's no software cheat, really. I essentially must buy and use ARM hardware running KVM.
Pretty much, yeah. QEMU and KVM together give you the fastest speed possible, but only within the strict bounds of matching processor types.
Yeah. What's remarkable, though, is QEMU's versatility in integrating with different hardware acceleration mechanisms across various operating systems. It's not just KVM.
No, QEMU's modular design is really key to its longevity here. It maximizes speed by plugging into the highest performing HVA or hardware virtualization accelerator available on whatever host platform you're using. On Linux, it's primarily KVM, which is highly mature and supports multiple ISAs, including x86, ARM 64-bit, MIPSS, and now RICV.
Okay.
On macOS, it utilizes Apple's native hypervisor framework, HVF. For Windows environments, it uses the Windows Hypervisor platform, WHPX. It can even integrate with Ven, which is another prominent Type 1 bare metal hypervisor typically used on Linux.
This wide compatibility really seems to confirm that QEMU's core strategic value today isn't its ability to translate the CPU anymore. It's that standardized, robust device virtualization layer that works everywhere.
Absolutely. If a new, faster hypervisor framework emerges tomorrow, QEMU can, in theory, just write a back-end connector to it. This ensures that its massive library of emulated devices, all those network controllers, disk interfaces, specialized peripherals, remains available to the next generation of virtualization speed solutions.
And it's essential to stress that this ecosystem extends far beyond just traditional x86 cloud data centers, right?
Oh, definitely. KVM's robust support for non-x86 hosts is driving massive industry shifts. Think about cloud-native ARM servers like the Graviton instances from Amazon and others. They rely heavily on KVM and QEMU.
Great.
Furthermore, the burgeoning RISC-V ecosystem, from tiny embedded chips all the way up to potential server farms, is largely being built on this very same QEMU KVM foundation for development and testing. QEMU is really foundational to the accelerating move toward more heterogeneous computing environments.
Okay, so with the CPU bottleneck largely solved by KVM delivering near-native performance, the focus immediately shifts. The next constraint becomes I/O. Data transfer rates, latency, the overhead of network and disk operations. This becomes the new challenge for maximizing overall VM speed.
Exactly, and this is where we really need to pay close attention to QEMU's device emulation capabilities.
Yeah.
If you stick with the baseline approach, traditional full software emulation for devices, well, the overhead is enormous.
Right.
Like, for example, emulating a legacy device like an old AC97 sound card, it requires QEMU to trap and translate every single I/O operation requested by the guest OS. This results in really high CPU utilization on the host and terrible latency for the guest.
So the virtual devices themselves need to be virtualization aware somehow. They need a faster way to talk to QEMU than just pretending to be old, slow physical hardware.
That leads us directly to the standard solution for high-performance I/O today. Per virtualization via Vertio. Vertio is a modern framework. Instead of asking the guest OS to use legacy device drivers, which QEMU then has to painstakingly translate, VirtIO requires optimized guest drivers.
Ah, special drivers in the guest OS.
Yes, these specialized drivers know they are in a virtual environment and they communicate directly with QEMU using highly efficient shared memory data structures.
And what are those data structures called again?
They're called VirtQs. These are essentially shared memory buffers that allow QEMU and the guest to exchange I/O requests and data with minimal overhead. It dramatically minimizes the need for QEMU to trap and translate those low-level I/O operations. This is pretty much the essential baseline for any high-performance accelerated VM today.
But for some environments requiring extreme throughput, we're talking enterprise networking, massive storage arrays, even running VirtIO through the main QEMU process might introduce too much latency, right? Because QEMU is still kind of in the middle managing the data exchange. What's the architecture's answer for maximizing throughput even further?
That's where the VOST user protocol comes in. This is really the next level of optimization. The goal is simple: offload I/O processing entirely from the main QEMU process to a dedicated separate component.
How does it do that?
The VOST user protocol shifts the VirtIO backend device implementation. That's the part of the device that actually moves the data to an external user space process, typically a separate daemon running on the host.
Why bother with a whole separate daemon process? What does that gain us?
Control and specialization. That external process, which is often built using specialized data plane acceleration frameworks like DPDK, can be designed purely for maximum speed. It can utilize highly aggressive techniques that wouldn't be appropriate for the main QEMU process or the host kernel, like busy polling.
Busy polling.
Yeah, where a dedicated CPU core just constantly checks for new data rather than waiting for an interrupt. It wastes CPU cycles, but minimizes latency. This results in extremely high throughput and remarkably low latency for I/O. Essentially, QEMU manages the control plane, setting things up, and the external daemon manages the high-speed data plane, moving the actual data.
Okay, here's where it gets really interesting, though, because this relentless pursuit of extreme speed introduces a very specific and quite critical security trade-off.
It absolutely does. The security implications of VOST user are paramount and, frankly, non-trivial. To perform high-speed direct memory access, or DMA operations, that external backend process needs to be able to move data directly between the guest's memory and the physical network or storage device.
And to do that,
It means the external process requires full, explicit access to the guest's physical memory.
oof, that sounds dangerous.
It significantly elevates the attack surface risk. If a vulnerability exists in that separate external user space process, which is now running likely with high privileges, constantly handling potentially untrusted network traffic, an attacker could potentially leverage that flaw.
And because it has full memory access.
Because the process has full memory mapping capabilities for the guest, a successful exploit could compromise guest data, leak sensitive information, or potentially even compromise the host system's integrity by manipulating memory structures it shouldn't touch. It's a very calculated risk. You get maximum speed, but you also get maximum complexity and an elevated security risk that you absolutely must manage carefully.
So system architects who choose VOST user are essentially accepting higher operational security risk in exchange for that near bare metal I/O speed. It's a pretty profound operational trade-off.
Absolutely. And QEMU also offers other specialized high-speed mechanisms too. For example, device pass-through. If the host hardware supports IOMU or VTD features, QEMU can configure the system to give a guest VM direct control over a physical device, like a dedicated GPU or a specific network card.
Bypassing QEMU entirely for that device.
Completely bypasses all emulation for that device. It delivers true bare metal I/O speed, but the big downside is it requires dedicated physical hardware that cannot be shared with other VMs or the host.
Right, one device per VM. And what about advanced multi-layer cloud architectures? Is there anything new there?
Yeah, there's an emerging feature called VirtIO VONS user, which really highlights QEMU's architectural flexibility. This model actually allows another virtual machine, perhaps a specialized network switching VM or a high-performance storage controller VM, to act as the VOST backend for other consumer guest VMs running alongside it.
Wow, VMs providing I/O services to other VMs directly.
Exactly. This complex setup can eliminate intermediate software layers and host network switching, potentially enabling new, extremely efficient ways of structuring I/O delivery within a cloud environment.
It's clear QEMU has evolved way beyond being a simple emulator. It's now this massive, sophisticated toolkit for managing pretty much every type of hardware interaction imaginable, especially things like storage.
It really has. QEMU provides complex block storage functionality, supporting formats like QCOW2, which is highly efficient, and enables dynamic features like live snapshots and live migration. And its flexible character device system, the SHARDIV subsystem, handles I/O for character-like devices, connecting them to standard input-o, TED-o files, Unix sockets, PCP networking. Really, maximum versatility for connecting things up.
Okay, all this complexity in QEMU is warranted because it's so deeply embedded in highly specialized professional workflows. Let's look at where it's actually used most often, maybe starting with the area where compatibility is still king.
Right. Outside of the big cloud virtualization use case, its primary domain is probably embedded systems development. QEMU is absolutely the standard tool for simulating ARM-based boards, MIPSheets boards, and increasingly RRSCV boards.
Why is this so crucial?
This simulation allows developers to test firmware, debug low-level drivers, and perform really early-stage development, often without relying on scarce, expensive, or sometimes completely non-existent physical prototype hardware.
So it just accelerates the entire development cycle by being a software stand-in for the hardware.
Exactly. It removes hardware constraints early on. It's also crucial for cross-platform testing and CI/CD pipelines. Organizations need lightweight, resource-efficient VMs to run automated tests for diverse platforms. QEMU provides the necessary infrastructure for continuous integration setups.
Allowing teams to test, say, ARM codebases on their x86 build servers.
Precisely. They can do that quickly, relying on the TCG mode even with its known speed penalty, because the flexibility often outweighs the clock cycles in that specific context.
Now, let's explore its specialized debugging capabilities. This is where QEMU gives low-level analysts some really profound control.
Yeah, QEMU integrates seamlessly with the standard GNU debugger, GDB. You can launch QEMU with a simple flag, -GDB PCP 3333, for example. This tells the emulator to pause execution and wait for an external GDB instance to connect over the network, exposing a standard interface for deep system analysis.
But there's one crucial flag that makes this truly powerful for security researchers, right? You mentioned it earlier.
Yes, the -S flag. This flag is critical because it tells QEMU to freeze the virtual machine immediately upon startup before the guest program executes even its very first instruction.
Why is that so important?
This is essential for security analysts, especially those using tools like PU tools for exploitation development. It allows the debugger to attach and set breakpoints deep in the kernel's initialization code, or maybe in a program's early setup routines, before that code has actually executed and potentially changed the system state or jumped into some protected memory region.
That level of precise timing and control must be the difference between catching a subtle vulnerability and missing it entirely sometimes.
Absolutely. Now, moving on to connectivity, QEMU offers a kind of choice between security and accessibility with its networking configurations.
Right.
QEMU typically manages network connectivity via two distinct topologies. The default, and generally most secure, is native networking. This configuration uses a virtual bridge on the host, often something like verbri0, and assigns private IP addresses to the guests. The guests can reach the external world via network address translation, or NAT. This prioritizes isolation and security.
But what if I'm running an externally facing server inside the VM? I need systems outside to be able to connect in.
Then you must move to bridge networking. This configuration is definitely more complex to set up, requiring you to configure a dedicated network bridge on the host operating system first, and then integrate QEMU with that specific bridge interface.
Sounds like more work.
It is, but the payoff is usually worth the trouble. The guests receive externally routable IP addresses directly from your network, allowing outside systems to connect to them just like any physical machine. This is pretty much essential for any kind of production server environment running in a VM.
Okay, finally, let's cover the dual management interface strategy. Cloud orchestration systems and automation tools need to talk to QEMU reliably using code, not just human typing commands.
Exactly. QEMU recognizes the need for both human and machine interaction. For human operators, there's the Human Monitor Protocol, HMP. This is a simple line-based interactive text interface. It's perfect for dynamic interaction, maybe state introspection, real-time administrative tasks, like typing in the command migrate TCP.192.168.1.4444 to initiate a live migration of the running VM to another host.
Simple and direct for humans, and for automation.
That's where the QEMU Monitor Protocol, QMP, comes in. This is a well-defined, versioned, machine-usable API based entirely on JSON serialization. QMP is absolutely indispensable for large-scale deployments, for cloud management platforms like OpenStack, and for ensuring stable programmatic control where reliability and automation are paramount.
Why JSON?
Because automation systems need predictable, structured output that they can easily parse. HMP, being text-based for humans, can't always guarantee that stability across versions or commands. QMP provides that stable, machine-readable contract.
We really must pause here, though, and acknowledge that the complexity of QEMU's command line interface is, well, it's notorious. Specifying every single resource like iShim4G for memory, NiShim2 for processors, plus every single virtual device, network config, storage file. It's initially a very steep barrier to entry.
It absolutely is. There's no denying that. But that complexity is in many ways the price you pay for the power it offers. It grants the specialist, the embedded developer, the security analyst, the cloud architect, unparalleled and incredibly precise control over every minute detail of the emulated hardware. If you truly need that level of granularity, QEMU is often the only game in town that provides it. Hashtag tag tag outrack ultra.
So we've taken a pretty deep dive into QEMU today, and what seems really clear is that its mastery lies not in just a single capability, but in its remarkable ability to manage that core architectural tension. It successfully balances cross-architecture breadth, mainly via the TCG's intermediate representation, with high-performance virtualization achieved through partnerships with KVM and other HVAs.
Right. And this is all possible because QEMU strategically decoupled the speed-critical CPU execution from the versatility-critical device management layer.
So the core takeaways for you, the learner, are pretty fundamental. Performance is inextricably tied to architectural homogeneity. Same guest, same host for speed. Cross-architecture compatibility is expensive, coming with that profound performance cost, potentially up to 35 times slower due to the generic IR layer.
And finally, the pursuit of extreme I/O speed demands accepting serious trade-offs in complexity and critically in security, as we saw in the necessary full memory access required by the VOS user protocol.
What's fascinating here, though, is that given that profound TCG performance limitation, QEMU's longevity seems to rest almost entirely on its robust, hardware-agnostic device abstraction layer now, not really its aging CPU emulator core.
Which raises a really important and quite provocative question for the future of virtualization. If the performance gap between the universal TCG and dedicated direct translation remains so vast, why should QEMU continue to pay that IR tax for architectures that are wildly popular, like by86 or ARM?
You mean why use the generic translator if you're just going by 86 to by 86 without KVM?
Exactly. Or even for common cross-translations. There are active proposals being discussed to add a kind of middle tier, a highly optimized direct binary translation approach specifically for the most common pairings. Think by 86 to by 86 or RM to ARM without needing KVM, and potentially even faster cross-translation for common pairs like that 86 to ARM or vice versa, bypassing the generic IR entirely for those specific cases.
So the big question is, will QEMU eventually shed the high overhead generic IR for its most popular pairings just to gain more speed?
Well, if the project embraces such a fundamental change, it would significantly redefine QEMU's identity. It would shift its focus, at least partially, from being the universal translator that prioritizes breadth and maintenance simplicity above all else to becoming more of a performance specialist in certain critical domains. That decision, sticking with universal compatibility versus chasing customized speed for popular architectures, is likely the next great architectural debate facing the QEMU project, especially as computing continues to diversify with ISAs like RSCV rapidly gaining dominance. The demand for both maximum compatibility and maximum speed isn't going away, that's for sure.